Olá, bom dia a todos e todas. Estamos aqui iniciando mais um webinário internacional, hoje com a presença e a colaboração com a França, intermediada pela professora Marlette, e o idioma oficial do webinário de hoje é o inglês. So, thank you so much. Good morning, everyone. It's such a pleasure to be here today and to introduce our speakers of today's talk. It's a huge pleasure for us, for Unifesp, to guest someone from France, because we know that France is extremely important in all different areas, but especially in physics. And also our universities is also developing the area of physics as well. So I would like to thank you, Professor Bastin, for being here. Professor Bastin is now in France, and she's going to talk about dark boson as a new force carrier. However, on behalf of the Graduate Studies and Research Office, I would like also to thank you, Professor Bassin and Professor Marlette Assunção. Professor Marlette Assunção is a partner of our webinars. I think it's almost the fourth or third webinar she's guessing and working as a moderator. She's been working hard behind the scenes to guarantee the best webinar for you today. And it's such a pleasure to introduce you, Professor Marlette Assunção. She is associated professor at the physics department at Unifesp Campus Diadema. She's employed since 2006, working in the area of nuclear physics and studies of nuclear reactions of astrophysical interest and nuclear physics problems involving radioactivity nuclei. She's coordinator of the scientific dissemination project Vamos Nuclear, and also she's in the leading of the course Introduction to Nuclear Physics and Applications offered since 2016. So Professor Marlette, thank you so much for being here today with us. Thank you so much for being working with us at Unifesp, and I can tell Unifesp is extremely proud of you and of your work to bring for us this opportunity to be in touch with Professor Ben Bastin. So I wish you a very pleasant and very learningful webinar today. Thank you so much.
Thank you, Camilo. Firstly, thank you, Professor Beyhan Bastin, for accepting my invitation so readily. I take this opportunity to also thank you, Professora Kanchan Kinshadani, for the partnership in organizing these webinars, Professor Camilo and Miss Sarah Commerce for the support in the organization. Only for the public, please put your questions in the YouTube chat. After the presentations will be read to our guest, okay? I present the Professor Beyhan Bastin is a research at GANIL, one of the most important inference laboratory in France and the world, okay? Beyhan did her doctoral thesis in fundamental nuclear physics at the University of Caen in France in the year 2007. The postdoctoral at the University in Leuven, Belgium, from the 27 and to 29. In that occasion, she proposed the measuring of the deformations parameters in nuclei in the experiment that was carried out in the CERN ISOD facility. In 29, she was hired as a full-time researcher by the CNRS and in the GANIL laboratory in France. Since then, she has been working on investigations related to nuclear physics, focus mainly on the study of the nova type supernova and core collapse of the stellar explosions. She is involved in many projects at GANIL and the other laboratories in Finland, Bucharest, Romani, among others. From 29 to 2016, uh, it, she was heavily involved in the development of the low energy branch of the super separators spectrometer, which is the part of the new Spiral 2 facility in France. Since 2018, he has focused in its research of the search of the new light gauge boson through nuclear physics measurements. Is developing the she is developing a scientific program of the topic in the Spiral 2 facility. Now, that I have introduced this research with the great dedication and success in the research. I invite everyone to listen to her. Thank you, Beyhan.
Thank you very much, Marlete. I would like to acknowledge the University of Sao Paulo and yourself a lot, Marlete, for the invitation. I will give this presentation on behalf of the New Jedi collaboration today. So my presentation will follow the following timeline. So I will first give you a presentation of the GANIL Spiral 2 facility where I am working on. I'm giving also the webinar right now. Afterwards, I will give you first a short introduction about the conventional description of our universe composition and assess the dark matter detection difficulties. This will allow us to come out to the presentation of our project, the New Jedi project, which stands for New Geodesics Experiment for Dark Sectors Investigation. For that purpose, I will just introduce briefly the dark sector theory. I will introduce also the beryllium-8 anomaly, which was somehow the starting point of this scientific program. And of course, I will give you a synthesis of the experimental activities that we have carried out within our collaboration and present you also our future plans. So the GANIL Spiral 2 facility is located in the northwest of France at the city of Caen. Where I am right now. So this here you have a top view of the Jules Horowitz campus where the GANIL Spiral 2 facility is constructed, is running. So here this is the existing, the historical GANIL facility, and here you have a top view, artistic top view of the Spiral 2 facility. And these two facilities is carrying experiment mainly focused on the idea to bring understanding about fundamental nuclear physics, but also nuclear astrophysics. There are also some experiments which addresses atomic physics and applied research topics like medical or industrial activities. And I am currently located here in the building of Engineer and Physicists of GANIL. And GANIL stands for Grand Accélérateur National Lyon-Lourds, and Spiral 2 stands for Système de Production Lyon-Lourds Radioactif Accéléré en Ligne, just for your knowledge. So I have started my presentation with this first slide, which presents the general layout of the GANIL Spiral 2 facility. I would like to acknowledge our current director, Patrice Rochelle-Thomas, who has provided me the great slides concerning our facilities. So I will present you the existing GANIL facility, and afterwards I will give you a description of our new facilities, Parallel 2, as you can see over there. So the GANIL facility is a particle accelerator whose technology is based on the acceleration of ions using cyclotrons. So here you have a bunch of 2 ion source that injects ions in the different cyclotrons. So there is a series of 2 big cyclotrons that we name CSS1 and CSS2. The first one allow an acceleration of particle up to, let's say, 10% of the speed of light. This energy is sufficient to allow the fusion of 2 particles to produce new ones, but also to transfer some nucleons to the projectile and target nuclei to produce new nuclei, radioactive nuclei. And if you increase, so if you inject instead of doing a direct interaction, if you decide to accelerate further the stable ions, so you can reach up to, let's say, 30% the speed of light, and this energy allow you to realize some reaction, fragmentation reactions. These reactions are very interesting because it allows to produce very asymmetric nuclei with very asymmetric number of neutrons and protons, and with a fraction of neutrons much more important than the fraction of protons. So you can produce very neutron-rich matter. And these nuclei have some specific properties. They are also synthesized on very explosive stellar environments. And this is very interesting because it's all these different possible radioactive nuclei with different configurations. They allow us to study the properties of the nuclei far from stability, so in a very unstable configuration, but it allows us also to reproduce in laboratory nuclei that are synthesized in stellar explosions, like novae, for instance. These ions are then distributed in a different experimental area of GANIL, where you have last and new technologies for detection system of gamma rays, charged particles, and that you can find some examples described over there. In the existing GANIL facility, we conventionally accelerate beams from carbon to uranium from an energy which is, let's say, from 1% to 30% of the speed of light. And what is very interesting is with this facility, with GANIL, you can carry it out in parallel for up to 4 experiments. That's very interesting. The new facility, as for it, do rely with a different type of technology to accelerate ions. So this time it's not a cyclotron that is used, but a linear accelerator, and in particular, it's a superconducting linear accelerator. So here you have a more detailed view of the new facility. So in this new facility, we already have 2 ion sources, one for light ions and one for heavy ions. We plan to have an additional ones that should allow us to have even much more better performances for heavy ions. And in this facility, we will reach something like 10% of the speed of light for the particles. Basically, we will have the same performances in terms of energy as the first cyclotron. The difference between the two is that the new facility will allow us to accelerate much more intense beams. So in the first facility, where you can accelerate something like microamps of beam, tens of microamps of beam, in the new facility, we can have access up to milliamp, and it will be one of the facilities that will provide the most intense stable beam in Europe and even in the world. So this is very enthusiastic, because this means that through this new accelerator, we will be allowed to realize the synthesis of very heavy elements and to realize a detailed spectroscopy of them. We will be able to have access to very intense neutron beams that could be produced, for instance, in the NFS facility, so Neutron for Science facility. It's a facility where the stable ions are sent in this converter room, where when the beam hits some material to produce neutron beams at a very high flux. I present you this room because basically, as a new JEDI collaboration, we plan to realize some measurement in this new facility, taking advantages of the high and intense proton beams and stable that can be provided by the linear accelerator to carry, we hope, our next experiments. This is the view of the time of flight room. And you have also another room, which is a room for the separator spectrometer, S-Cube, that will allow us to produce heavy elements and produce nuclei which are neutron deficient, which have a fraction of neutron and proton close to 1 and a bit higher. And in the near future, we will have also an additional experimental room who will also a new detection system allow the spectroscopy of nuclei produced in these facilities. But this facility will be also connected to the existing GANIL and could benefit of the ions that could be produced with the large target units, what we call spiral 1. So these two facilities will be connected in fine. And this is a very, if you need to realize the full visit of the GANIL facility, you need something like 3 hours without losing time. And this is a very good laboratory for students to acquire skill on very broad instrumentation side, and also acquire some skills about the different aspects of physics. So now we switch to the scientific program that on which I am working on right now, which is the study of the existence of a dark boson. Before entering the discussion, I wanted to present you first, for people who are not familiar with the nuclear astrophysics topic, I wanted to give a slide that summarize a bit the conventional description of our universe. So here you have a kind of distribution of how we estimate the universe is composed of. The ordinary matter, what I call ordinary matter, is basically the stars, the planets, the interstellar gases, and so on, that we used to study in an intensive way in the nuclear astrophysics, but astrophysics community. This ordinary matter represents just 5% of the universe composition. We have then 26% made of dark matter. When we say dark matter, we would rather say hidden matter, in the sense that we have observed some anomaly on the rotational speed of galaxies, for example, which can be just explained by introducing the existence of an additional matter. And we also have observed some effect like gravitational lenses, which confirms the existence of this hidden matter. And then through the observation, we have, for instance, observed that we have an accelerated expansion of the universe, and the major force in playing a role in our universe is the gravitational force. This force is an attractive force, so it's a force that has a tendency to bring together the different masses. And here, to explain the fact that we have an accelerated expansion of the universe, something like acting at the opposite way of the gravity, we needed to introduce the concept of dark energy. The different fraction between the ordinary matter, and dark energy have been deduced from the study of the analysis of anisotropies in the temperature of the cosmic microwave background that you find over there. That has led to reward Jean Peebles for a Nobel Prize in 2019. So the first peak here, you have the fluctuation of temperature as function of the angular size. To understand the first peak, we need to consider that we have a flat distribution of our of the visible universe. The second peaks indicates that we have some 5% of ordinary matter. The second peak tells us that we have 26% of dark matter, and the remaining fraction corresponds to the dark energy. So the point is, over the last 3 decades, since we have indication of dark matter, there were and several candidates like the weakly interacting massive particles. A lot of investigation has been carried out, experimental programs to prove in order to be able to detect these dark matter particles. Here is a non-exhaustive list of the main experimental program that you can find over the world, which aims to detect these particles. However, up to now, over the 3 decades, there hasn't been really a clear experimental proof of these dark matter particles. There is a kind of very interesting exercise that has been carried out in the US, and also the same type of exercise has been carried out in Europe. You have the 2 references over there, which is called the US Cosmic Visions and the Physics Beyond Collider synthesis and perspective work. And through this work, and in the very recent decade, has come out the idea to consider an alternative approach of the universe functioning. And this is this alternative approach that we as a New Jedi collaboration try to investigate. So this approach is based on the idea that the fact that we do not observe directly dark matter particles may come basically from the idea that we don't interact directly with them, but rather with an intermediate particle, which is called the dark boson. This dark boson acts basically as a messenger of the interaction between ordinary matter and dark sectors of the universe. And our aim is to study the existence or not of this possible portal between these 2 sectors. So we have carried out very recently, when I say very recently, it's from June to July, we got something like 7 weeks of experimental run in Paris, where we have realized the first experiment. I will show you today, later on, and on this presentation, some spectra we obtained online. And to run out such a big experiment, we needed the support of additional persons. So here you have the list of the core plus extended collaboration. So extended means people who provided helps to be able to run out such a long experimental run. So the core collaboration is somehow synthesized over there. So I am the scientific coordinator of this project. I see rather myself like a boson, so I'm the person who will allow the interaction between all these different persons. Here you have the list of the co-spokesperson of this project together with me, which are listed over there, which are basically the representative also of the different facilities where we run out our experimental program. So New Jedi experimental program is distributed between 3 facilities. We have realized our commissioning in Czech Republic at Prague, using a Thundertron, the new Thundertron located at Res. This commissioning has been realized last year, basically. We have realized the first experiment on barium-8. I will come out to this one this year, and we plan in the near future to realize the next experiment in the GANIL Spiral 2 facility. And in complementary to this experiment, we investigate the existence of the dark boson. We have also an experiment, a complementary experiment, which aims to clarify some nuclear structure uncertainty on beryllium-8 that we plan to realize, we hope, beginning of next year. So for this collaboration with colleagues from South Africa, we have received some specific funding from the French Ministry of Foreign Affairs and the Ministry of Higher Education and Research from the French side, and the Department of Science and Innovation and the National Research Funding in South Africa. In the collaboration, when we realize the experiment, there is an important part, which is the targets. So you need a beam, but accelerated particles, but you also need targets. This activity is done successfully by our collaborators from Catania, which plays a major role in this collaboration. And we have also in a collaboration worldwide expert on the dark sector theory, such as Pierre Fayet and Maxime Pospalov. Maxime is one of the co-spokespersons of the project. We have also experts on the Beyhan nucleosynthesis and nuclear structure theory. So this is a huge collaboration, but somehow we have a kind of a clear overview of the activities of different partners. So now we come to the dark sectors. When I have reminded you on this section the conventional description of the universe, and despite its apparent complexity, if you look to a star or whatever, all the ordinary matter, at the end, it's composed of very simple particles, which are quarks and leptons, and together with gauge bosons, which allows the interactions, and also the Higgs boson. So it's basically they're just few elements. And this standard model, which describes pretty well the ordinary matter, is not able to describe hidden sectors of our universe. And then came the idea to have the possibility of an indirect interaction between ordinary matter and hidden sectors. And in this formalism, in this study, we define dark sectors not like the sum of the dark matter plus dark energy, but rather like a hypothetical set of relatively light particles with an interaction which is orders of magnitude lower than the electromagnetic interaction. So what do we mean by that? I have presented in this slide the four well-known forces of nature that are the gravity, the electromagnetic force, the weak force, and the strong force. In red, is indicated the boson, so the particle that allows the interaction in the framework of these different interaction. And in white, I have specified basically the relative intensity of this interaction with respect to the strong force. And when the interaction we're considering here is something that might be close to the weak force in between the electromagnetic and the weak force. So it will be basically probing the idea if there is an additional fifth force of nature. So this is a very important take-home message. So we don't detect dark matter particle. We are looking to the fact that there is a particle and there is a set of hidden sectors, hidden set of particles that may or not contain dark matter particles. So this it's a very new concept. And depending on the quantum nature of these particles, we may have different possible bosons, different possible portals. And in red, I have indicated the different dark bosons, the different portals that we can, as a nuclear physics community, investigate. This theory in this general form has been introduced around the year 2004, 2008. So you have some references over there. Of course, there have been some studies that have been carried out earlier, for example, in the 80s, like the studies carried by Pierre Fayet, in order to investigate, for example, the existence of a dark vector, so which is named also dark photons. But the theory in its general form has been really considered a bit later on. So every year we have an annual workshop meeting, and prior to these meetings, we provide to the audience and to the students some kind of lecture series on the different theoretical aspects of the project. And last year it was not last year, but I already switched to 2023. So this year it was a lecture of Pierre Fayet, and next year we will have lectures from Maxime Pospalov prior to a workshop that takes basically in May every year. So I cannot give a very detailed review about all the different possibilities and studies that have been carried out for the different possible portals. I will just take an example of the dark photon. So this is one of the portals that has been extensively studied in the community, scientific community, and even in the 80s. It's basically not because this is the most probable or this is the most favorable one. It's also because from a theoretical point of view, it's the one which is the easiest to calculate and also the easiest to compare with experimental results. So in the case of a dark photon, I have plotted here the epsilon. So this is a kinetic mixing parameter. It's just a parameter that gives somehow the intensity of the interaction as function of the mass of the boson. So how much the dark boson, the dark photon will couple as function of its possible mass. As you can see, most of the experiments leads to define exclusion zone. They say basically, okay, we haven't observed a signature of a dark boson from our experiments. This means that the probability is lower than this or higher than that, and the mass range that we have thrown is this one, so it cannot be within this mass range with this intensity. What is very interesting is that if we look to all the experimental results, is that there is an experiment that has been carried out on the beryllium-8, which is known as a beryllium-8 anomaly. It's an experiment from an Hungarian team located at the Hungarian team, the Atom Key Laboratory, Krasznahkai and collaborators. This is a group which has allowed a very strong constraint on the mass of a dark boson. So this is the red line over there. In this graph, you have a lower and upper limit. The lower and upper limit for epsilon is not something coming out from this experiment, because this experiment has basically allowed to set a lower limit for the epsilon parameter that you can see over there. It's just basically the theoreticians who wanted to go further from this measurement, and they decided to take as an upper and lower limit the result from the anomaly magnetic moment of the electrons, and from an experiment which is E141, which aim to look for the search of dark photon via Bremsstrahlung experiment. And there have been also some recent measurements carried out by the NA64 collaboration at CERN. And if we take out also the result from the NA48 experiment at CERN, which aim to investigate the existence of the production of a dark boson through the decay of the pion, we end up, if we want to include all these experimental results, we end up to consider a dark boson which is photophobic, which means that it couples more with neutrons than photons, which is a kind of strong hypothesis. So what happened using this experiment, basically how they ended up to determine such a precise mass of the dark boson, they just ended up basically a proton beam at an energy of 1 MeV, which corresponds to 5% of the speed of light on a lithium target. At this energy, they realize the fusion reactions that leads to the production of beryllium-8 in an excited state. This nuclei then decays, so it needs to reach out a more stable configuration, following three different possibilities. The first one is the emission of a photon. The second one is emission of a photon and the creation of an electron-positron pair. So since the electron and the positron which are created, since the photon do not have a mass, the momentum is very high, and you have a small angle between the electron and the positrons, and the distribution follows somehow these trends. It depends, of course, on the electromagnetic nature of the photon. The shape will be a bit different, but somehow you will have a curve like this one. And if this beryllium-8 decays through the emission of a dark boson, in this experiment, the dark boson has been deduced to have a masses of 17 MeV. This dark boson has a very short life. It decays very instantaneously to an electron-positron pair. But in that case, you have a very specific angle between the electron and the positron, which leads to have such a kind of distribution. The angle basically is something around 140 degrees. So if you look to the experimental spectra, so this is basically the number of counts a function of the angle theta, they obtain such a distribution with a kind of bump on the spectra. And this bump can be only explained by introducing the possible decay of a X particle, of a dark boson, of a mass of 16.6 MeV. So if we consider a lower mass or higher mass, they were not able to reproduce the experimental spectra. So I have put it here, the different mechanism that leads to the production of an electron-positron pair. And here a simplified scheme of the beryllium-8 excited states. And this is a transition that leads to the production of the dark boson. And I have also synthesized here other properties that has been measured from this experiment that were very also important in order to deduce some properties of this dark boson. And this experiment has allowed to reject only one hypothesis, so one quantum portal, which is a scalar portal, because due to spin parity conservation, this is very technical, I'm sorry, but the other portals are possible. And these are the references, some example of references where this experimental result has been considering a vector, so the vector of the scalar boson. So this is, if you look to the spectra, considering this free portal over there and excluding this one based on quantum spin parity conservation rules. So the beryllium-8 system is a very complex system, as you may see over there. And what is very interesting is there is some 2+ states that you can find on the level scheme, which have some specific properties. This is called, in the theoretical point of view, exceptional points. And it's kind of strange that through the decay of these states, there is not really a play, the role of these states are not really taken too much into account. And the idea is to probe in our collaboration how these two exceptional points may bring some interferences or contribution on the experimental results. We have also the idea, and we have also already carried out some measurements to clarify the electromagnetic nature of the transition, the gamma transition. We have seen that some of the E2 component were not basically taken properly into account. And so we are planning to do new angular distribution measurements, and also to see if by hazard there is not also a possible hard gamma-gamma process entering into account in such a decay. We are in strong collaboration for this scientific program with some theoreticians such as Peter Navratil, who is currently realizing some ab initio investigation based on the experimental results of the measurements we carried out last year, or even the year before. So this group have specified the existence of the anomalies they have in beryllium-8. They have also investigated the existence of this anomaly in other quantum systems, like carbon-12, helium-4, in order to constrain more the quantum nature of this particle. But somehow the different experiment has not led to identify clearly the quantum nature of this dark boson, of this anomaly. And therefore came out the idea that maybe the production of the X17, so the dark boson, it was named also X17, may rather go through may not rather go through a nuclear resonance. So it can be a non-resonant production decay. So this is the reason why, since you just have one group of getting very important and interesting results, as for the Higgs bosons validation, there were two groups from CERN who have observed in parallel using different methods, different decay scheme, the signature of the Higgs bosons, and independent measurement is needed. So since then, so there was a huge interest in the nuclear physics community. It's very interesting because here are the list of the future project which aims to realize and to probe the dark photon hypothesis. And what we can see is that in the MEV range, there is an area where there is not so much investigation that has been carried out. This is the MEV range, and this is basically the range very suitable for nuclear physics. The main reason is basically because this kind of physics was really the interest of the high energy particle physics community, and not so much from the nuclear physics side. So even though if the community intention is very focused on this area to cross-check if the anomaly exists or not in this at 17 MeV, it's very nice because we can have, as a community, a broad investigation of this area, and this is something that should be maybe developed in the incoming years to extend the investigation on this area for which we have the expertise. So we have entered this topic in 2017 under the call of Maxime Pospelov and Alain Koch, who has identified also the point that the nuclear physics community should have a look on this aspect. And so we have realized some test experiments in 2018 and 2019 at the Aramis Cap facility located at Orsay. It's in the south of Paris, at the IGC Lab laboratory. Complementary to that, we have realized some geometry simulation. So here is a scheme of the detection system that we have developed. So we have a set of two double-sided silicon strip detectors that allows us to identify the angle of the electron-positron pairs emitted from the reaction of a proton impinging on lithium beam, basically. And then we have a set of plastic detectors that measure the total energy of this particle after passing through the silicon detector. So we have the angle and the total energy of these particles. This is the first setup that we used for the commissioning last year. So this is a picture of how the target look like and how they were set in the first target holder. And before getting the beam, we have mainly done offline characterization using radioactive sources, such like bismuth-207. Then it's very interesting because we ended up choosing the same technology as the atom key group. So the first result on barium-8 were deduced from using multi-wire proportional chamber detectors, and they switched to silicon, and we switched basically to the same technology at them, just to let you know. And for this specific experiment, we have developed, we have used some digitizer developed by GANIL, and also developed some method to cross-check the proper synchronization of the digitizers over time, because here the most important parameter is to check that the two particles are really correlated on time. This is basically the level scheme, the electronic scheme that we use for this experiment. We have also developed new charge to digit converter digitizer option for these digitizers, and that is presented here. For the experiment we have carried out at IGC Lab. So this year, sorry, we changed a bit this electronic skin to get something which has a higher resolution, and that will be presented in an incoming presentation. So just to let you know, so this is how New Jedi was set at the beamline in Czech Republic. So you have a picture of colleagues setting the targets. This is how the lithium fluoride target look like, and this is how it shines when it is heated by the beam. And we can even have an accurate pink spot measurement thanks to this interaction. So we can define in a very accurate way where the reaction occurred on the target, as you may see over there. So this experiment was carried out during the COVID time, and you have some picture of the collaboration working hardly in order to solve the different problems we observe all the time. And these different problems are listed over there. So during this experiment, every milliseconds, we have produced something like hundreds of beryllium-8 nuclei, and only few per minute could be assigned to the production of a Higgs boson, if it exists, if we consider the production probability given by the atom key group. We have observed that there is a huge contribution from this reaction, that the lithium target emit a lot of electrons of low energy that we had to deal with. We observe a lot of multi-scattering processes that we need to go also to master and to understand. And we have also cross-checked that the method that we developed to measure and check the proper coincidence between the different detectors worked pretty well. We have tried new target configuration that should allow us to realize in the near future new complementary measurements. And we have also observed very interesting geometrical effects that we are investigating and understanding through some new simulation that we have carried out the last weeks. Based on all this, and thanks to the modification we have carried out during the commissioning, we were able to move the New Jedi setup at the Andromède facility, so located at Orsay in France. New Jedi was mounted at the 1 degree beamline over there. So for this experiment that lasted 7 weeks, we have used something like hundreds of target units, so it was really a lot. Thanks a lot the Antonio in particular for the active production of and the very clean production of the targets. We have brought some modification for the plastic detector geometry, and this is how the new geometry of the New Jedi setup look like. So we have sent a proton beam of 300 nanoamps in average on a lithium fluoride target. We have used the double-sided silicon strip detector to measure the angle between the electron and the positrons. Using the plastic detector, here you have an example of the spectra we obtain the number of counts per 6 minutes, and we can see that we observe in a clean way the resonances of interest on beryllium-8. You see here you have the 18 MeV. We have also observed the resonances coming from the reaction of the fluoride inside the target. We placed outside the chamber detector to monitor the target composition. You have the same spectra, but with a higher resolution. And this is the spectra of the energy loss observed in one of the strips of the silicon detector. So over there, it's very interesting because if we compare the shape of the spectra over there with the simulation, we can see that we can also realize some additional selection because the energy loss coming from the electron positrons from an X17, so dark boson decay, would not release the same energy. So we could also, if we think that there is a signature of an electron positron pair linked to the decay of X17 boson, we can cross-check from the energy loss in the DSST if it's compatible or not. So this is a kind of additional check that we realize we are able to carry out from our measurements. We have a very low threshold, something like 200 kV, below 200 kV, which is large enough to ensure the proper detection of this electron-positron pair. Of course, we have not yet the experimental results. So the students who will carry out the data analysis is arriving tomorrow evening, basically. I'm going to take him at the airport. So we have, of course, results from simulations, and this is a spectra we expect basically from our experiments. If we find out the same properties as the Hungarian group, here you have the invariant mass, which corresponds to the total mass of the X17 from our experiment. So if this is an invariant mass coming from an X7 signature, we should see a peak over there. And if it's coming from the other process, which is the internal part creation, it should have the following shape. So we should be able to see this peak over there. And we have our setups cover just the angle of interest from the X17 decay. And we should observe such a shape from our electron-positron opening angle spectra. So now that we have realized this measurement, what is the timeline of our collaboration? So we plan to carry out our first experiment on the study of the structure of beryllium-8 next year. Basically, I should shift this arrow over there. We plan to go through the GANIL Scientific Council in order to get more resources to carry out such experiment, because this is very long and very demanding experiment that it requires more resources, human resources, but also financial resources. And based on the recommendation of the GANIL Scientific Council, we will go through the realization of the first experiment at Spiral 2, or discuss about the idea to realize a second experiment, complementary experiment at Andromeda. I would like to thank the students who are currently involved on the data analysis or simulation of this experiment, which are Damiano, Sabia, and Ignacio. I would like to show you how the new JEDI should be integrated for the Spiral 2 experiment. So we have already prepared the integration of the experimental setup in the new linear accelerator. So here you have the view of the superconducting LINAC. And I would like to finish to address some acknowledgements to the technical staff from GANIL, UGF, INFN, LNS, and also IGC Lab for the support, for very crucial for the success of the experiment. You can, if you're interested in project, you can follow the activity of our collaboration on my Twitter accounts. I'm really giving some news, fresh news. So currently we have shut down the setup for the winter, and we realized some last calibration measurements, and we will restart in January to realize and to do some modification on the plastic detectors. And you also have on YouTube some videos which explain you in a very simple way the underlying physics, and also provide a presentation of our collaboration. Thank you very much for your attention, and I am ready to answer your questions.
Okay. Is the new curiosity about this theme. I have the question. I look at the question of the YouTube. There is Alexandre Alves asking about what the kind of the nuclear physics effect could explain the atomic anomaly. Are there prospects to hunt for this X70 in E plus E minus collisions facilities?
It's an excellent question. So basically, I will answer because there are two questions. So if we look, as I said, to I will come back maybe to the slides of lithium beryllium-8 over there. Yes. So the problem is beryllium-8. It has a very complicated nuclear structure, as you may see over there. And in order to do a proper distinction between the electron positron coming from the internal perturbation and the Higgs boson, one need to know very well the electromagnetic nature of the underlying transition. And basically, if we look on the literature, the characterization of this electromagnetic transition have been carried out in the 16th. And if we look to this work, the angular distribution method that allows this characterization, the spectra were not so clear. This is the reason why it pushed us to realize some additional measurements. According to our result, it should modify a bit the shape to consider for the subtraction of this peak. We don't expect somehow to be strong enough to modify the existence or not of this anomaly, but it is really important to have it set properly. For example, in the different branching, the decay for these 2+ states is not really considered properly. It should affect a bit these results as well. This is something we would like to investigate, but we don't believe that it will somehow give a strong answer to the question if this bump comes out in a very crystal clear way from the existence of a dark boson or not, because there are some also corrections, efficiency corrections that needs to be done basically.
Wow.
And we have observed a lot of multi-scattering processes during the experiment. We also have observed from the simulation and our understanding of different behavior between the electron and positrons behavior with the different detection systems. And these are corrections that needs to be taken into account seriously. We have also observed that important relativistic corrections should be set in. So this is not very obvious to answer this question, because we need to master different experimental aspects. And this is the reason why it takes us a lot of time. And also, in order to avoid all this uncertainty linked to nuclear structure, we believe that it would be wise to consider the study of the existence of this Higgs boson in much more much more simple quantum system, like helium-3, where there is basically no excited state, and where we could say we have or not the dark boson signature. And this is basically where we would like to go through, and this is what we would like to investigate as a collaboration as the next experiment. So this is the first part. The second part is about doing electron-positron reaction directly. And this is an excellent idea. And I would say this is something that if we were able to do, this is something that should be done. The difficulty comes from the realization of such experiment. You need to produce a positron beam. And to my knowledge, there is only one group, which is a PADME collaboration, who try to reproduce this reaction. The problem is that they have something 200 MeV beams, and they gave a presentation during the INPC conference where they specified that they are facing some background issues, some technical issues, and they need some developments in order to be able to carry out a proper investigation of this signature from their experiment. But basically, this is also an interesting probe. For the moment, the people who can do that, let's say in the closest way, the fastest way, are not so ready to. Okay.
Okay. Her more question. Kanchan Kenshadani asked, are there other nuclear physics reactions where we can expect to see the presence of the X17?
Yeah, basically, because the last investigation, so if you look to this area, they have realize the investigation in other quantum systems like carbon-12, helium-4, and we plan to go through helium-3. Since there is not a clear picture, basically the idea is to say, okay, it's not a resonance decay from a resonance production of the X17, and therefore it's a non-resonance production. And as long as you have an 18 MeV or 17 MeV boson decay threshold, you should be able to investigate this study.
The Igor Luis Montavani Rigoto said comment that was amazing, your webinar. And
Okay.
one question, in the longer run, how could this impact or possibility change our comprehension of the universe expansion?
This is a good question, and this is one of the questions I like to address myself basically when I have free time, when I call a positive procrastination session as a researcher, because there is also a theory which is called the ground unification theory. And in this theory, the idea is that all the forces are linked together at the beginning and then they split. And here, if you introduce an additional force, it has to enter into account in all the processes. And this is very interesting. Then if we show that there is existence of an additional force, and once we would have, if it exists, identify its quantum nature, to see how when it enters into account in all the nuclear evolution. And this is basically a very interesting aspect that should be taken into account, but for the moment it's too early. We first need to, before going through such a deeper consideration, we should first see whether there is something really serious to consider.
Alexandre Alves commented, this is a golden target for our Nobel Prize.
Yeah, she is right, basically. But this is also a problem, basically, because when you tackle such a question, and there is already some serious hints, experimental hints. As a nuclear, as a researcher, the question that I'm always asking myself is, am I seeing what I want to see? and for that purpose, it's very it's important to be not doing the work on your own. And this is good because we have a big collaboration. We have every week a weekly meeting, and we really exchange in a transparent way the different information. And by the way, we have set an electronic logbook for this experiment, and once we will carry out the data analysis, we will leave the data on open access for everyone. So because for us it's also important that all the community could cross-check the work we did. And I'm also happy that there is a group using different method, different technique, and that will investigate the subject. And if we have a lot of the very strong contribution from the community, we can definitely bring. And if it exists, basically, it was the right choice to focus a bit in on nuclear physics or activity on that field, which is not the historical field of interest of nuclear physicists. But as you may see here, the point is this area hasn't been investigated, and we are the best to probe this area. Yeah.
Okay. And Kanchan Kishadani said the mass and the width of the X17 are of the same order. Finding a signal of such a particle should be challenging. It's the comment. Okay.
Yeah. I haven't understood properly the comment, but can you repeat it, or
you could said see in the chat, but I repeat the mass and the width of the X17 are of the same order. Finding a signal of the search particle should be challenging.
Yeah, it's challenging, but hopefully, if we look to the detection system, the way you need to have a clean signal is to have a lot of coincidences between different particles. So you need to have a coincidence between two detectors, silicon strip detectors, and another one between the plastic detectors, which has a good time resolution. What is good also for the experiment that we will carry out at GANIL, we could also have a coincidence with a beam particle because it's a pulse beam that we have. So the fact that you need 5 signals in coincidence giving you these results is some kind of high selection, and this is the fact that we could realize all these constraints should allow us to say, okay, we have done a proper work.
Okay.
It's challenging, but we have the tools to clean up properly the spectrum.
This is my question. What is expected to improve in the experiment using the Spiral 2?
Yeah, the advantage of the Spiral 2 facility is the fact that we basically the experiment in helium-3 needs something like 20 MeV beam. And this is something that you cannot really have access easily on small tandem as accelerator. So this is kind of energy that you realize in cyclotrons, big cyclotrons. And the problem is for this experiment, we need to change the beam energy to do some measurement at different energy. And this is something difficult to be done in cyclotrons. And therefore, the fact that we can do it in less than 1 minute in our accelerator of Spiral 2 is something very important and useful for us. And it's very stable, and we have also pulse beam. So this is basically, to my knowledge, the only place we can do it properly. And this is the reason why we would like to carry that at Spiral 2. So we will have an additional connection with respect to the tandem accelerator, and we'll have more flexibility with respect to the cyclotron accelerators. So, and I would say I don't see any place where to do it in that way. So.
Yeah, about the analysis, how is the analysis of the experimental data from a new Jedi experiment begin divided? You coordinated?
Yeah, it's a very good question. So we have something like 32 terabytes data. It's a lot. So among the 7 weeks of data, we have something like rather 3 weeks and a half of pure clean data. So we will have the main student Ignacio doing that, and we will ask some people from the collaboration to give independent set of data, those which have nothing to do, and to check if we find back the same results. So this is kind of exercise we plan to do. So we will also maybe ask for some advertisement from some advices from high physics colleagues, how they do, for example, for such rare signals analysis and signature. And everything will be then distributed in an open access, so people could look and even comment or change themselves and have a look if they find the same results. And this is, I think, this is interesting also to be able to share all this, and I think it's a good way to ensure that we didn't make any mistake. So, but we can do mistakes, but it's good that others can also have a clear view on that and some criticizes on it. If you want, we can.
Thank you, Beyhan. It's very nice webinar. Thank you, merci beaucoup. and now finish the transmission. Okay.
Thank you very much. Thanks for everybody for listening carefully.
Okay. Thank you.
Bye.